Hello again. In this video, I'm going to go over section 2.5, which is about limits at infinity. So to illustrate this idea of a limit at infinity, suppose you have the graph of a function f of x that looks like this. Let's try to determine what the y value is approaching as x heads towards infinity. So for this particular x value, the corresponding y value would be right here. And then as x gets bigger, I think you can see that the y value gets closer and closer to this number L. So in this case, we would say the limit of f of x as x approaches infinity is equal to L, and this is known as a limit at infinity. By the way, notice here that you also have a horizontal asymptote at the line y equals L. So if you have a limit at infinity that's equal to a finite number, then you also have a horizontal asymptote at y equal to that particular finite number, in this case L. You can also have a limit at negative infinity. So let's suppose x is approaching negative infinity. Let's see if we can't determine what the y value approaches. So for this x value, there's the corresponding y value. And then if you let x approach negative infinity, you can see that this y value is getting closer to this finite number m. And so we say the limit of f of x as x approaches negative infinity is equal to m, this finite number m. And again, notice that you have a horizontal asymptote at y is equal to m in this case. Okay, so if you have a limit at infinity that's equal to a finite number, just remember that you also have a horizontal asymptote at that number. In fact, the horizontal line would be y equal to that finite number. Okay, so that's what we mean by a limit at infinity. Now let's just look at this example 1. This is a limit at infinity. I guess technically it's a limit at negative infinity. And let's see if we can't figure out what this limit at negative infinity is. Okay, so to evaluate this limit, what we can do is we can break this up. We can find the limit of this first piece and then add it to the limit of this second piece. Okay, of course this limit's just equal to 2, because as x approaches negative infinity, the output for this function is always 2. But what about the limit of this function? Well, as x is approaching negative infinity, the bottom piece down here is the magnitude of it is just getting larger and larger. So for example, if I were to plug in negative 10 squared is 100. Now I let x get closer to negative infinity, so you plug in negative 100, well then you would get negative 100 squared here on the bottom. And so I think you can see that this is going to be a 10 divided by an increasingly larger and larger number, which means this is getting closer and closer to 0 as x gets closer to negative infinity. Okay, so this limit here is 0. And so overall, the limit is 2 plus 0, which is just 2. Now let me show you the graph of this so you can get a visual of it. This is the graph of the function that we're working with. And we're approaching negative infinity, or x is. Okay, so let's let x approach negative infinity. All right, for this x value, there's the y value. If you let x get closer to negative infinity, the y value is now here, and the closer you get, the closer the y value gets to this value of y is equal to 2. And so that's this limit. Okay, the limit of f of x as x approaches negative infinity in this case would be 2. And by the way, that's the location of a horizontal asymptote at y is equal to 2. By the way, if we were to find the limit as x goes to positive infinity, we would also get 2. Because as x gets larger and larger, you can see that this y value is creeping closer and closer to 2, positive 2. Okay, so that's the first one. That's the first limit. Let's see if we can't find the second one. So again, we can break this up and find the limit of the first one and then add it to the limit of the second one. Okay, of course the limit of this is equal to 5. Okay, now we need to find this limit. So here's how we're going to find this limit. We're actually going to use the squeeze theorem. Okay, so sine of x is always trapped between 1 and minus 1. And what we're going to do is we're going to multiply this compound inequality by 1 over the square root of x. Okay, so multiply each of these by 1 over the square root of x. Now, one thing to note is you do not have to flip the inequality, and I should write this as a less than sign. You do not have to flip the inequality because this is a positive number. And we know this is a positive number because x is heading towards positive infinity. And so when I take 1 over the square root of a positive number, it remains positive. Now again, if this was a negative number, I'd have to flip the inequality. But if x is going to infinity, then we know that this 1 over square root of x is a positive number. So we don't have to flip the inequalities here. Okay. And so we're actually going to use the squeeze theorem to find this limit. Remember the squeeze theorem, you have to find a lower bound function and an upper bound function. This is my lower bound function, and this is my upper bound function. And then so there's two conditions. The first condition is to find the upper and lower bound functions. So that's condition 1. And then the second condition is you have to show that the limit of both of those, the lower bound and the upper bound function, are equal to the same number. So let's look at the limit as x goes to infinity of both of these lower and upper bound functions. Well, as x is getting larger and larger, 1 over the square root of x is heading towards 0, so this limit would be 0. And that's the same for this. So both of these are approaching the same number, right? They're both approaching 0. And by the squeeze theorem, that means the limit of this function that's trapped between them must also approach 0. So if this is heading towards 0 and this is heading towards 0, as x heads towards infinity, since this function is trapped between those two functions, that would mean this would have to head towards infinity. So by the squeeze theorem, we know this limit would be 0. And so overall, this limit would be 5. Now, a quick look at the graph of this function. The graph of this function, 5 plus sine of x divided by the square root of x, looks like this. And so you can see as x goes to infinity, you can see it's oscillating, but as it goes to infinity, it's oscillating over a smaller and smaller range. And so it begins to approach 0 because the range that it's oscillating between becomes so small that it's, I'm sorry, not approaching 0, approaching 5, right? It begins to approach this line y equals 5. Okay, which by the way is a horizontal asymptote. So it has a horizontal asymptote at y equals 5. Okay, so I think there's a couple things to remember here. When you're working with limits at infinity, if a limit at infinity ends up being a finite number, like in this case it's 5, then we also know that there's a horizontal asymptote at the horizontal line y equals 5. So just remember there's a correspondence between these two ideas. Now, next time we'll look at, there are some cases where when you find the limit at infinity for a function, it is possible not to get a finite number. Maybe this is equal to infinity, or maybe negative infinity. Okay, so it's when you're finding a limit at infinity, you're not guaranteed that that would be equal to a finite number. It is possible that you could have a limit at infinity that actually ends up being infinity or negative infinity. And so we'll look at those cases in the next video. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.